All right. Okay. I was just talking to Dr. Judd about the fact that we're pretty far behind, so I'm probably going to be moving relatively fast today. So if I start going too fast, raise your hand, slow me down, but I'm going to be cooking. So
With canola oil.
olive oil.
Avocado oil.
I haven't ever had that.
It's way better.
All right, distracting me. We got to move. As always, we're going to do prairie organisms of the day: prairie grass, prairie forb, and prairie animal. Prairie grass of the day. This is Indian grass, Sorghastrum nutans or newtons. It's another C4 grass. We won't talk about nothing but C4 grasses. We'll throw in some C3 grasses as well, but a lot of the grasses at Kanza are actually C4 grasses. That will mean more to you when we get to that point in covering the Kanza Prairie case study. It's once again one of these perennial bunch grasses. If you guys recall, out at the glade, it was the most common grass that you saw out at the glade. A number of you asked me about it while we were out there. This thing sends out rhizomes, which are just essentially underground stems. It's one way of reproducing vegetatively, so it can grow in these big clumps where everybody's related. It gets pretty tall. It's a major forage grass on prairies. This is one of the grasses that bison love. Once again, it has a really deep root system, very similar to the root system of big blue stem. Baptisia alba is my favorite indigo. Indigo, you also saw these out at the prairie, and you might have also seen some of these out at the glade as well. That's a different variety of Baptisia, which is Baptisia purpurea, which is the purple indigo. My favorite is the white indigo because it has these pretty white flowers. It has the pinnately compound leaves that are common for the family Fabaceae. The family Fabaceae is the legume family. These are plants that produce seeds and pods, and they also have root nodules. And in these root nodules are bacteria, soil bacteria, that live in close association with the legumes. And these bacteria are nitrogen-fixing bacteria. So they take nitrogen out of the air and they transform it into a form that is absorbable by plants. And so whenever you eat beans, that's a good source of protein because these plants are capable of fixing nitrogen because of these symbiotic relationships that they have with nitrogen-fixing bacteria. It has a wide range around the United States. I have this in my front yard, and so you can also commonly buy it for landscaping, things like this. The prairie animal of the day is the black-tailed prairie dog, Sinomys ludovicianus, and if you ever are in Oklahoma at Wichita Mountains National Wildlife Refuge, it's a great place to live, and there's a section there where there's a road that goes right through the middle of a prairie dog town. So there's prairie dogs on both sides, and they get enough human traffic that they will come right up to you, and you can get awesome pictures of prairie dogs. These things are known as ecosystem engineers because they alter ecosystems in large and fundamental ways. In the case of these guys, they actually alter ecosystems by basically bringing nutrients that are deep in the soil to the surface of the soil as they go through the process of constructing their prairie dog towns. And it becomes so pronounced, it's a little difficult to see here, but this is me on top of the hill looking down on the prairie dog town that is at the Wichita Mountains. And what you can see is that the vegetation where the prairie dog town is located is totally different from the vegetation just adjacent to that prairie dog town. And that's because they've essentially churned up the soil in such a way that it has created a local environment that is suitable for some types of plants and less suitable for other types of plants. And so this interdigitating boundary of this large patch of flowers also demarcates the boundaries of this prairie dog town. They are preyed upon by hawks and eagles, and they are also preyed upon by coyotes when coyotes can sneak up on them, and they are also preyed upon by things like badgers and ferrets in certain parts of their range. So they have a series of predators that feed on them, and then they also have these kind of large-scale effects on prairie vegetation because they disturb the soil in ways that alter nutrient availability. These yellow flowers that are in the background in this photo are actually the yellow flowers that are making this outline. All right, questions about those guys? All right. Those are not in the slides that are posted. Dr. Judd and I are going to be putting all of the prairie plants and animals into a single slideshow that we will post so that you can get those all in one place. You'll also notice that on Moodle that this particular PowerPoint is divided up into 3 sections, and it's because Moodle wouldn't let me upload it as all one thing because it was too big, which is why hopefully we're going to be getting something other than Moodle to manage our courses. So I asked you guys to think about seasonality in weather, in climate, and we just passed the autumnal equinox here back in September. And the equinox, basically equinox means equal night is what it means in Latin. And the equinox is when we have a 12-12 photo period. And there's a 12-12 photo period everywhere on the face of the earth. 12-12 photo period at the Arctic Circle, at the Antarctic Circle, and every spot in between. And we reach equinox in the spring, in March, and in the fall, in September. And then we reach solstice in December and summer. The vernal equinox, not the vernal equinox, the summer solstice and the winter solstice. And in the summer solstice in the northern hemisphere, that's when we experience the longest days. So back when you were hanging out in June and July, the days were really long. You could stay out late, and it was still light out. And we're moving from the summer solstice through the autumnal equinox towards the winter solstice, which is in December. That's when the days are shortest, the nights are longest in the northern hemisphere. And then after we pass that solstice, we start moving back towards equal day length, and then we move to the longest day length. And so we do this every year. What's the primary reason that we have this kind of seasonality on the face of the planet? It should be obvious from this figure. Okay, so the orbit of the Earth around the Sun is on a flat plane. What is the rotational axis of the Earth relative to that plane? Sonia? Yeah, it's canted. It's tilted 23.5 degrees. So that as the Earth moves around, there are times a year when that axis of rotation is perpendicular to the sun's rays coming towards the Earth. That's when we get the full surface of the Earth lit by an equal amount of sunlight in terms of time of day duration. Then there are some times when the axis of rotation of the Earth is tilted parallel and towards the sun, in which case we have long days in the northern hemisphere and short days in the southern hemisphere. And then there's another time of year when that axis of rotation is tilted parallel to the sun's rays, but tilted away from the sun, in which case we're experiencing shorter days in the northern hemisphere and longer days in the southern hemisphere. And so it shouldn't surprise you that if we think of the Earth as an angle from equator at 0 degrees and the North Pole at 90 degrees, At 23.5 degrees north and south, that's the latitude of the Tropic of Cancer and Tropic of Capricorn. And 90 degrees minus 23.5 degrees is where the Arctic and Antarctic Circle is. And so that degree of latitudes for those markers that we put on maps frequently is due to this 23.5 degree tilt of the Earth. And so that's what leads to seasonality. If we didn't have that cant, we wouldn't have seasons. The equator would just always be getting the most sunlight of anywhere on the planet. We would be getting less sunlight, but it would be constant throughout the year because the amount of sunlight that we get isn't influenced by where we're positioned around the sun, because the axis of rotation would be perpendicular to the plane of revolution around the sun. So this is why we have seasonality. But when sunlight comes to the Earth, all sorts of things happen to it. Only a fraction of it actually gets down to the surface of the Earth, because a lot of it is absorbed and scattered and reflected by the atmosphere. And so when we think about the sunlight that is available for plants to do photosynthesis, we have to think about how thick the atmosphere is that the sunlight is going through, because only about 40% of the atmosphere that hits the upper parts of the atmosphere actually make it down to ground level. The rest of it is absorbed, scattered, reflected, goes someplace else. So when we think about how much sun is actually striking the surface of the Earth, the amount of solar energy is influenced by three primary factors. Photon density refers to how dense are the photons as they hit the surface of the Earth. So imagine that if the sun is hitting the Earth at a 90-degree angle, and there's a 1 square meter area of sun coming to the Earth through space, when it gets to Earth at the equator, that 1 square meter of photons is hitting on 1 square meter of the surface of the planet. On the other hand, if you have a 1 square meter area of photons coming to the Earth at higher latitudes, either higher latitudes north or higher latitudes south, when that hits it, it doesn't hit at a perpendicular angle, it hits at an oblique angle. And so you take that 1 square meter of sunlight and you're spreading it out now across a much wider area. So when it hits the surface of the Earth, the actual number of photons per area of Earth isn't the same as it is flying through space, because it gets spread out across the curved surface of the Earth. So at higher latitudes, whether it's north or south, you have less sunlight because the total density of photons is fewer. What else is happening to light as it goes from space down to the surface of the Earth? Yeah, why is that? Who said that? Yeah, why is that, Emma?
Because space is pitch black.
Okay, so there's nothing in space, so it's just coming at us from space. When it gets to the upper surface of the atmosphere, how much atmosphere is it going through here versus here? Versus up here. From the surface of the atmosphere down to the ground level. Yeah.
Based off the angle it's coming directly at doesn't have as much of a surface.
So it's going through a thinner atmosphere here. And it's not that the atmosphere differs in its thickness around the Earth, it's just that the path of the sunlight through the atmosphere is shortest in the tropics around the equator, and it's longer as you get further and further away from the equator. As a result, you're going through a thicker and thicker section of the atmosphere, so there's more opportunity for absorption, scattering, etc. And that then makes sunlight more intense at low latitudes and less intense at high latitudes. It also makes sunsets nicer at northern latitudes than at southern latitudes. And then the last thing is reflection, and reflection is a little harder to understand, but how many of you have ever been to the lake? Okay. When you're at the lake in the evening, what does the surface of the lake look like? Speak up. It's very reflective. Why? Yep, the angle. It has everything to do with angle. So pretend that the sun is green. The sun is not green, but you're standing at the lake, and the sun is low in the sky. The photons coming from the sun are hitting this lake at an oblique angle. And what happens when that happens is a lot of the photons get reflected off of that surface, and very few photons actually penetrate into the lake, simply because of the fact that they're striking the surface of the lake at this oblique angle. And you're going from a less dense medium into a more dense medium, and things like light tend to glance off the surface of dense mediums when you're moving from a less dense medium into a more dense medium. When you're at midday, what does the lake look like? It looks kind of like the sky. Well, you're basically getting most of your photons are now penetrating. Some of them are still reflecting back, but most of them are penetrating into the surface of the water. As a result, you don't get that reflection of sunlight coming off of the surface. You're actually just then getting the reflection of the color of the sky off of the surface. And so the degree of penetration into a denser medium is going to be influenced by the angle of incidence. In the same way, we have a really not dense space, and when it hits the more dense upper surface of the atmosphere, some of it will penetrate, but at these high latitudes, more of it is just going to glance right off the upper surface of the atmosphere because it's hitting it at this low angle of incidence, whereas a lot more of it is going to penetrate near the equator because it's coming at it at a perpendicular angle rather than a really oblique angle. For these three reasons, we have a lot more solar input down around the equator than we do as we move away from the equator towards the two poles. More energy means more energy for things like photosynthesis to occur, so that affects primary productivity, the amount of photosynthesis that's going on, but it also results in differences in heat distribution around the Earth. So there's more light at the equator, there's more photosynthesis at the equator, and there's more heat at the equator. Everybody get that? All right, cool. Well, what this does is as the Earth heats up, the surface of the Earth also heats up, and it heats so the sun is coming in, the surface of the Earth is heating up, but as that's happening, the air adjacent to the surface of the Earth is heating up. And as that happens, that warm air rises. And so it creates this low pressure because that air is warming, it's expanding, and as it expands, it rises. It goes from down near the surface to up higher in the atmosphere. How many of you guys have ever been to the beach at an ocean? Okay, where's the wind always coming from on the beach? It's coming from the land or is it coming from the water? It's always coming from the water. Why? Stay at the beach, the sun is beating down. Sun is beating down on the water, sun is beating down on the sand. When you're walking from your beach towel to the water, what do you have to do in the middle of the day on the sand? Yeah, I always said that. Oh yeah, you have to move fast, right? Because the sand is really hot. When you get to the water, what is the water like?
Cold.
It's cold. It's cooler than the sand, and sometimes it's cooler by a lot than the sand. Well, the reason is that water has one of its physical characteristics is that it's capable of absorbing a lot of energy without changing its temperature much. It's what's called in chemistry and physics high specific heat. So water warms up much more slowly than something like sand does. So what is the temperature of the air right above the water? Hot or cold? Okay, so this is going to be cooler air because this is cooler water. What's the sand and the air going to be like here? It's going to be hot sand and warm air above the sand. As this warm air rises, it creates a kind of a vacuum, if you want to think of it this way, and it's going to pull in air from where? It's going to pull the cold air in that is adjacent to it. Same thing that happens at a beach happens globally. As this warm air rises, it pulls in the air adjacent to it. Because the warm air rises, it creates this kind of lower pressure. That lower pressure pulls in air from the adjacent parts of the earth. As this air rises, it cools. What does cool air generally do? It wants to sink, but this air can't sink. Why not? It's not hot. It's cooling as it goes up in the atmosphere. But that cool air now that wants to fall back down because it's denser can't. Why? What's underneath it? All this hot air rising. So that hot air, as it rises, it cools, but that cool air can't just sink right back down because there's still this massive hot air coming up. So what does it do? It slides off of that massive hot air coming up, slides off towards the poles. When it finally is off of that hot air mass rising, it begins to descend, and it descends at about 30 degrees latitude. And so here you have warm, moist, rising air, and here you have cool, dry, descending air. And it sets up this cell of circulation called a Hadley cell. What do we know? What kind of biome exists around the Earth at the equator? Tropical what? Yeah, but what type of biome occurs there? Is it a desert? Is it a forest? Tropical rainforests. Tropical rainforests occur around the equator because this warm rising air that is moist, because warm air holds more water than cool air does. As this warm air rises, it picks up water, but when it gets higher in the atmosphere, what does it start to do? It cools, and as it cools, it condenses into clouds, and it eventually rains. And so where you have this warm rising air, you also have a band of increased rainfall. It rains itself out as it cools, so that you're descending over here at 30 degrees latitude, and that descending air, it's cooler, and it's also drier because it's rained itself out down here around the equator. That air coming down pulls in adjacent air that sets up a second cell of global circulation. As this air comes back to the atmosphere, it's running along the surface of the Earth, and the whole time that it's traveling along the surface of the Earth, its close contact with the surface of the Earth is causing it to warm back up, so that by the time it gets back to the equator, it's warm enough to rise again, and also it doesn't have this cold air mass holding it down the whole way. This air circulation sets up this air circulation, descending cool, dry air at 30 degrees. It warms up, picks up moisture, and rises up here at about 60 degrees. And that cell of circulation sets up this cell of circulation. And when we look at this, if we were to flatten the Earth out, we would see warm rising air around the equator. It rains itself out, it cools, and it descends. Cool, dry, descending air. Cool, dry, descending air warms up, gathers moisture around 60 degrees, rises, causes another band of rainfall. How many of you have ever been to Seattle? Nobody? Anybody ever been to? Okay, what is Seattle known for?
Rain.
It is known for rain. Guess at about what latitude Seattle sits? It's up there at around 60 degrees, north latitude. There's just over the bay from Seattle is Olympic National Park. It is a temperate rainforest, and there's a rainforest that occurs there because you happen to be at this latitude where that second warm rising moist air is rising and it falls down. What kind of music came out of Seattle? Famous music for Seattle. Nirvana. You guys ever hear of a band called Nirvana? You ever listen to the lyrics of Nirvana songs? Really? Listen to them. They're depressing. Okay, now that I said that they're depressing, oh yeah, I have listened to Nirvana songs. No surprise that Nirvana formed in Seattle. It's cloudy, it's rainy. When it's sunny at the University of Washington, such that you can see the mountain, there's a mountain, is it Mount Rainier? No, not Mount Rainier. Mount Rainier. So there are certain days during the year when you can see Mount Rainier. At the University of Washington, a campus-wide email goes back that says the mountain is out. People cancel classes because it happens so rarely that you can actually see the mountain from campus. It rains a lot in Seattle, and this is the reason why. Then it sets up this third cell. By the time you get up to the North Pole, that's a really cold air, really dry air. We normally associate the poles with all of this ice, so we tend to think that it's snowing there all of the time. But what's happening is that snow is just snow and ice that is built up over long periods of time. And in theory, if we weren't messing up the world, it's always there and it doesn't really ever melt. Because this is actually a polar desert. They get similar rates of precipitation that deserts get, but because it's frozen precipitation and because it's always cold up there, it just tends to stick around for long periods of time. So you tend to have tropical rainforests, deserts, temperate rainforests, and polar deserts. And the intervening places represent a gradient from really moist ecosystems to really dry ecosystems to really moist ecosystems to really dry. And so there's this continuum, and somewhere in the middle between these is where grasslands occur. So for me, the easiest way to remember this is to think about a true color picture of the Earth. And I've got the equator here, I've got 30 degrees north here and 30 degrees south here. And when you look at the global distribution of deserts, what you see, if you go to North America, you see the Great Bison, Mojave, Sonora, and Chihuahuan Desert are located around 30 degrees on the west side. The Atacama Desert, one of the driest deserts in the world, on the west coast of South America, once again at around 30 degrees. The Saharan and Arabian deserts are straddling 30 degrees. The Great Victorian Desert is straddling 30 degrees. The Taklamakan and Gobi Deserts is a little further north than 30 degrees, but that's mainly because you have the Himalayan mountains here that kind of pushes those deserts up further north. Yeah?
How come it's just on the west side and it's not on the other side?
You are still in my glory. That's a very good question. Why do they tend to only occur on the west sides of continents? That literally is going to be my next question. Thank you for playing right into my hands. Is position on the face of the Earth in these global atmospheric circulation patterns the only thing that affects climate? What else can affect climate? Well, that's what we just did. We talked about this, right? Why do we have tall grass, then mixed grass, then short grass prairies, going from east to west? Yeah. Not really. We're not. Yeah, not until you get into the foothills of the Rockies does that matter. And by which time, prairies have gone away for the most part. Yeah. No, but thank you. That's a good guess. That happens to not be the case. No, not even close. I mean, well, sort of close, but much more indirectly. The spinning of the Earth affects the movement of water. So, for example, the Earth is spinning this way, and so actually ocean levels are higher on the east coast of continents than on the west coast of continents because the spinning of the Earth kind of pushes water to the west. And so that's part of it because you're at the very beginning. So the spinning of the Earth changes how water flows, and water flows influence kind of the direction of flow of water in the northern hemisphere and the southern hemisphere. So does anybody know what direction water is flowing off the east coast of the United States? What was that? So if the Earth is spinning this way, that means water is going to be moving this way. So if water at the equator is moving this way, what is this water going to be doing? Is it going to be going up the coast, or is it going to be coming down the coast? It's going to be coming up the coast. If water is coming this way, is this going to be going up the coast or down the coast? Down the coast. So that water that's moving this way is being warmed by the sun, right? So this means that this current is going to be warm or cold. This current is going to be warm or cold? Warm. Like, whoa, we were on a roll there and then we broke down. As it moves north, it gets up here, and what starts to happen to it? It starts to get colder, so that when it comes down this side of the continent, it starts out cold, and then it starts to warm up as it gets down here, but it starts out cold. So we go from warm to cold to warm again, warm to cold to warm again, but along the west coast, it's cold. Cold water evaporates less than warm water. We talked about this back in the Galapagos. Remember that the Galapagos Islands, where is it socked? It's right over here in the middle of this normally cold oceanic current coming up from the Antarctic, passing along the west coast of South America. And so normal weather for the Galapagos Islands is dry. And it's because cold water evaporates less, there's less moisture in the atmosphere, you get less rain. And so you tend to have deserts around 30 degrees, but they tend to be aggregated on the west side of continents because water here is flowing here, it hits Africa, and it goes south, picks up cold water, becomes cold down here. As it's coming back up to Southeast Asia, as it passes Australia, it's cold water, cold atmosphere adjacent to the water, less atmospheric moisture, the tendency for deserts to form. So it isn't just this that affects climate, it's this combined with this. Global circulations of oceans as well. And it's what leads to this gradient of moisture from the Gulf Coast, which is where the warm Gulf Stream goes up the east coast of the United States, and pushes this gradient of moisture from moist to drier as you move from the southeast U.S. to the northwest U.S. And that's what accounts for this gradient of moisture. Look at this distribution of moisture and think back to the distribution of the prairies. Good. If you ever go surfing off of the east coast of the United States, which by the way is terrible surfing, but if you ever see people doing it, they're doing it in shorts. What are people doing when they're surfing off the coast of Southern California? They're in wetsuits because it's cold there. Thank you. I was able to bring in surfing references. Awesome. Dude. So, we can quantify weather by graphing the interaction of temperature and rainfall. And San Diego is a place where temperature is relatively warm throughout the year, although it doesn't get really hot, but it goes through a pronounced dry season. This is what leads to Mediterranean types of climates. And so these types of diagrams are basically trying to chart temperature versus rainfall in ways that represent when ecosystems are water stressed, when the rate of evaporation is higher than the rate of rainfall. And that's what these types of tan areas where evaporation exceeds precipitation. This is Philadelphia, Pennsylvania. It gets good rainfall throughout the year. It never gets too terribly hot because it's kind of on the north side of things. But it doesn't get a ton of rainfall relative to how much is evaporating. Belém, Brazil is a tropical rainforest where it gets tons of precipitation relative to a relatively constant temperature. At Kanza, you have temperatures that get fairly warm on a monthly average during the summertime, but you also have good amounts of rainfall through all parts of the year except for winters. Winters tend to be on the dry side, but because it's winter and it's cold, you tend to have also low levels of evaporation. And so while it's hot and relatively dry, it's not dry like a desert is. So if you go to San Diego and you leave town, you immediately get into the Mojave Desert outside of San Diego as you move to the east of San Diego. So we can use these climate diagrams to get a quick look at what kind of climate is in different places. And you will see deserts often exist at water deficits throughout the entire year. And so this is useful in measuring these things. At Kansas, there are not only yearly fluctuations in moisture, but there are also long-term fluctuations in moisture. And so this is a long-term weather data set from Manhattan, Kansas, which is just north of where Kanza is. And what do you notice right here, starting in 1932, 33, 34, 35 was an exception, 36 and 37. What's happening during this time period in history? It's a big drought, obviously, because it has low rainfall, but this is the Dust Bowl. So in the Midwest, in the 1930s, there was this prolonged period of drought. That prolonged period of drought led to the Dust Bowl, coupled with poor agricultural practices that made the topsoil unstable. These farms lost a lot of their topsoil. And once again, this is all because Kanza this section of the United States happens to be kind of in that range of temperature and moisture where it doesn't suffer a water deficit on normal years, but if it ever gets a year where it doesn't rain very much, it doesn't take much to push this section of the country into drought conditions. And then if you get that year after year after year for a period of 4 or 5 years, it really then affects plant communities such that the plant communities aren't capable of holding the soil in place. And then your topsoil blows away, and this is what you're left with, and it makes it really difficult to farm. So implications of long-term variation in temperature. Note that we don't get this long-term variation in rainfall rather. We don't get this low rainfall very often, and when we do, it's usually just 1 or 2 years. We don't get this long protracted period of reduced rainfall typically. Kanza. Prairie regulated and maintained by 3 factors: climate, bison grazing, and fire. Bison grazing is a thing. These are bison actually on Kanza. So you guys thought about this a little bit in your homework. What kind of influences might bison have on nutrient cycling in the prairie based on your homework of making observations about Kanza? Yeah.
They can overgraze and eliminate grass.
So they tend not to overgraze. They tend to graze an area, and then after they've grazed it, they move on to another area. But while they're there grazing, they certainly graze selectively on some species than other species. As a result of that, they can change plant community structure, and that plant community structure change may influence the available nutrients that are there.
They're restricted to an area. Is that area?
Well, historically, they haven't ever been restricted. And even within Kanza, where they are fenced within a large area, that large area is large enough that they move around as a herd, and they'll graze in one area, and then they'll go graze in another area, and they won't come back to those areas. And as soon as you burn it and new grass starts coming up, they migrate to that area immediately. So one way in which you can affect nutrient cycling is by affecting the types of plants, especially if you like to eat warm season C4 grasses, and as a result you leave forbs like indigo plants in place that are nitrogen fixers, then those things keep producing nitrogen because they're not being grazed down by bison. How else can bison affect nutrient cycling? Yeah, Sonia.
Well, would they like fertilize the grass?
Fertilize your grass how?
Like when they poop and the nutrients go back to the
Yes, so they excrete, they poop and pee, and that poop and pee is rich in nitrogen and rich in phosphorus. That then becomes incorporated into the soil, and that can affect, especially at a very local scale, the nutrient supply in soil. What else, Sam? Not in small amounts. It's full of nitrogen, so in that way, if you have a system that is lacking nitrogen, urine could actually boost the nitrogen content there. That's because they go there and they pee there every time you take them out. Over and over and over and over again, then you get too much nitrogen and that begins to kill your grass.
Okay.
You need to train your dog better.
My dogs don't do that.
Yeah, what else?
Doesn't that also affect because like bison they eat a lot of like nutrients from the ground that help in the soil, and like with that they eat a bunch of processed stuff.
Yeah, so they're eating plants, and then they tend to redistribute what they're eating by walking around the prairie and pooping and peeing it out somewhere, sure. How else can bison affect nutrient supply? This is not the obvious one. You've hit the two obvious ones. Not seed dispersal, although in a very indirect way, I guess that could work. Sometimes they die. And when they die, there's this death ring around this carcass. It's easy to understand why the plants are dying right underneath the bison, but why are the plants dying out to the sides of the bison? They're releasing all of their nutrients to the soil there, and in the same way that when your dog pees in the same place over and over and over again, plants can die when they don't get enough nutrients, and plants can also die when they get too many nutrients. And so there's this death zone around where nutrient content is too high, but as soon as you get out a little ways, what's happening to the plants? They're doing really well because now they're far enough away from the carcass. Nutrient supply has declined to the point that it's not killing them anymore, but it's higher nutrients than further out from the bison, and so you tend to get this increase in vegetation out at the edge. And the people at Kanza have studied bison carcasses over time. So nutrient cycling is affected by the activities of bison. How does this result in heterogeneity? So one of my first questions for you is, when I use the word heterogeneity, what am I referring to? How would you define it? Heterogeneity. Sonia. Okay, so heterogeneity just refers to differences as you move around in space. Is there heterogeneity in this class? Let's say heterogeneity in terms of the presence of head hair. No, there's not. Presence? I'm the only bald dude here. All the rest of you have head hair, right? Okay. So if we think about hairstyles, there's quite a lot of heterogeneity because we have sections of the class where there's long hair. We have other sections where there's shorter hair back there. So there's differences in hair lengths. There's no hair up here. Differences in hair length in different parts of the class. Depending on where people are sitting, you get little pockets with long-haired people, little pockets of short-haired people, and one pocket of no-haired people up here at the front. So that's what heterogeneity is. This differences that you find across any sort of landscape that you're thinking about. And you can think about it in the course of the landscape of a classroom, the landscape of a school, the landscape of a college a city, or you can think about it as the landscape of a prairie. So how does nutrient cycling maybe lead to increased heterogeneity in a prairie? And I'm thinking in this case of heterogeneity in plants. And I'm now tired of hearing from Sonia because she has been contributing really well today. So you're on mute for the rest of the day. Stop carrying the rest of the class. That's a good thing, actually, when you're put on mute. That's a positive thing. For you. Oh, I'm going to give you points. I'm keeping track of people. I'll award things at the end. How do the activities of bison with respect to nutrient availability influence heterogeneity? Yeah,
There's
Emma.
not the overproduction of plants, so there are plants coming out of plants.
Repeat that?
There's not an overproduction of plants. Like, for instance, in the forest, there was honeysuckle and that killed out a lot of other plants. So let's say they use one plant, it'll prevent overproduction of other plants.
Okay, so that's plant competition. In this case, it's for light, though. I'm thinking more of soil nutrients, but you're headed in the right direction. Think about soil nutrition.
It's not a competition for nutrients, not one species is competing than the other because their species are being multiplied by bison.
So any place a bison is pooping and peeing, what do you have? Nutrients, nitrogen, phosphorus. So any plants that need those things can survive and thrive there. Back to Emma's point, and Emma is also raising a good point. When a bison eats a bunch of blue stem or a bunch of Indian grass, what does that mean for the shorter stature plants on the prairie? They can grow because they have more light. So she was talking about light competition in honeysuckle. You can also have light competition in a prairie. It's just a shorter forest in a way. So one of the ways in which bison increase heterogeneity is they're disturbing the environment, but they're disturbing the environment not in uniform ways, but in very local ways. Very different than going through the prairie with a mower where everything gets cut down to the same height at the same time, and it's all uniform. Bison move from place to place. They have particular plants that they like to eat. They have other plants that they don't like to eat. And as a result, it leads to this patchy disturbance. And you won't be turning anything in at the end because we just talked through it. So disregard that last thing. Wallow is another type of disturbance. What are bison doing in these wallows? Sam? They're not rolling around in mud. They're not really cooling down. What's that? Because that's muddy. But these wallows are not generally muddy. These wallows are what? Emma? They're dusty. They're doing what horses and cows do. They roll around in the dust. They coat their skin with dust. That cuts down on skin parasites. What does that do to plant communities, though? It kills them. It gets rid of them. And in an active wallow, it'll just be dust. And when it rains, it becomes muddy. But one of the things you find is they don't wallow around in it when it's muddy like that. Actually, cattle and pigs tend to go down into stream bottoms when you're growing them. Bison tend to avoid stream bottoms, and they're up on the hot parts of the hill generally. It's a fundamental way in which cows and bison distribute themselves in a landscape. Cows like to hang out around waterways because there's shade and trees there, and bison tend to be up in the hot sun on the hillsides.
Mud is usually for cooling down, whereas the dust is
for parasites. So I do know why this is in here. Fire is the last thing. Fire is what they are manipulating, and grazing, the presence of grazers. And once again, they're varying fire frequency, the return frequency of fires, by dividing this up into watersheds and burning one watershed once every year, once every 2 years, once every 4 years, and once every 20 years. So what kinds of effects do fire have on a landscape? Sadie?
It can be really positive. I used to live on a farm and we actually fires every 2 years because so the bugs would do like a brush.
Mm-hmm.
A lot of things that aren't supposed to be there can start growing and getting into the environment. So you burn the trunk so that the roots have the like the right stuff in it and like regrow to it.
Okay, so in Kansas, if you go to Kansas in the spring, from about February until April, you will see all parts of the Flint Hills are on fire. Ranchers burn the Flint Hills because it burns off the old vegetation, allowing the new vegetation to grow up. One of the things it does is it kills off the woody vegetation. So if you left Kanza Prairie alone and never burned it, it would slowly over time return to a woodland. But fire kills those woody plants and prevents them from taking over. Why does fire destroy woody plants but not destroy grasses? Sorry, I heard two things. Kid?
They hide in the soil. They keep the roots in the soil.
You're on the right track, but not quite correct. Sadie, you were saying something. No, somebody said something.
I said the same thing, but they have deep roots.
So it isn't about the roots. Do you guys know what the term meristem means? Anybody see this word in high school? You feel like you've seen it. Okay, a meristem is the part of the plant where it's actively growing, it's actively lengthening its stems. In a plant like an oak tree or a hedge, where are the meristems located? They're located at the top, good. So if you were to draw a picture of a woody plant, you'll see meristems at the tips, and you'll also see meristems at the axils, where stems come off. And so when a fire comes through here and burns that down, it essentially kills all of the meristems that plant has, and so it can't grow anymore. Where are meristems located in grasses? Not in roots. Well, there is a root meristem, but the meristem for growing up, it's not in the roots, it's in the stems, but it's located right down at the soil surface. And so when you have grass growing up, it's pushing up from down here. When you cut your lawn, how many of you have mowed your parents' lawn? Seen your parents' lawn mowed? That's more accurate. When you mow your lawn, right after you mowed it, it's nice and uniform, isn't it? It's all chopped off, and the blades look like this. But then when you come back in a couple of weeks, and this has grown up, the top of the blade still looks like that because it was cut off here, and it's growing not by growing from the tip, it's growing by being pushed up from the meristem that is located right down here at ground level. So when a fire blows through a prairie, it destroys the meristems of woody plants and forbs, but it preserves the meristems of grasses, which are located down at ground level. We won't go into that. We don't have time. Never mind. I was about to talk to you about hedge clipping, but yeah. No, not at all.
When the buffalo eat it, the grasses, do they eat the meristem or not?
No, they crop it off actually fairly high, kind of like a lawnmower set on the highest setting would be. So they leave the meristems in place as well. So that's one effect of fire, is it affects the mixture of plants because it selectively kills some types of plants and leaves other plants intact. What are other potential effects of fire? Think about nutrients.
Brings back nutrients to the soil.
So that's complicated. Some nutrients do get returned to the soil as a consequence of this, but a lot of the nutrients actually just get volatilized as the thing burns. So as this is burning, in the smoke that is rising off of this, there's certainly soot, charcoal coming off of this, but there's also carbon and nitrogen, phosphorus and potassium and all those things. And then the residue that is left behind also has nutrients in it, and it tends to break down faster because you've kind of destroyed the carbon structures that hold that in place normally, but you've actually lost a lot of nutrients. It's just that the nutrients that do remain behind are going to be released to the soil faster than they would if the thing was just decomposing after it died or went dormant. So fire also leads to nutrient loss. And fire creates heterogeneity. So some areas, a fire will burn through and burn everything, and in other areas there won't be enough fuel to fuel a fire through that area, and that area will be relatively unaffected. This actually happens to be a fence dividing a place that is ungrazed and a place that is grazed by cattle. And the place where cattle have been grazing, they've reduced the fire load to the point that when the fire got there, there wasn't enough fuel load to carry the fire through there, which then created some areas that got burned and other areas that didn't. These are some of the watersheds at Kanza after they've been burned. They're surrounded by roads so that it stays within that area and doesn't jump over to another area. When we talk about watersheds, watershed is a place where all of the water that falls down in rainfall here is going to leave this watershed through this stream down here at the bottom of the watershed. So this is higher elevation, this is lower elevation, and this is the stream that drains this entire watershed. If water falls on this side, it's going to flow downhill and leave the watershed down here in this stream. So when we use the term watershed, that's what we're meaning. All right, we've already talked about heterogeneity, so we don't need that. And now I've taken up most of Dr. Jett's time. Any questions about this? Okay, that's the introduction to things, and we've covered a lot of ground. Each of those things that we've covered, we're now going to go through in greater detail. And Dr. Jett is going to start that process with you now. Or you? That is you. Yeah, okay, good.
Of the bison with the nutrient loading on it, that's on the plants for special years. That's what they wanted to show you real quick as I get started. This summer I was in a short grass area up in North Dakota, and
Oh, yeah.
this is going to relate to one of our ideas we're going to talk about in a little bit. This bison has been dead for a bit longer than the one just sown. There it is. And so the nutrient loading around it is diluted a little bit, and now it's actually a really nice place for certain species of plants to grow.
It is just right for those guys.
Yeah.
Yeah.
And then this is another one that we're going to relate to. This is an old wallow. We were on a trail walking towards the bison. Couldn't go any further without getting close to the bison, so we turned around. But when we turned around, there was an old wallow. And I started looking at it, and I took a picture. And right on the edge of the wallow, you can see this has been muddy, so the bison aren't there anymore. But a few certain species that are not occurring in the shortgrass prairie are starting to grow in that area where the bison don't go up. And I'm standing right at the edge of the wallow. So a couple things that I want to share you keep in mind as we go through this wallow. So, John Quincy introduced you to a concept a little bit ago of disturbance. And disturbance ecology is almost its own discipline within ecology. So, we're going to dive into a little more detail what disturbance is and how it relates to this other process called succession. I'm just going to introduce you guys to this, but what I want you to know by the end is what ecological disturbance is. What we mean by that term, disturbance, in an ecological context. What is a disturbance regime? The term that I've used before that I thought might be good to actually define this time. From previous semesters. And then what is ecological succession? And how is it different from other kinds of ecological change? Well, let's just start with a vocab program, I suppose. What do we mean by disturbance in the context of ecology? Well, a couple of definitions here. One is one of the characteristics that unites these is that something happens to change the composition of the community, what species are present. So a punctuated or discrete event that kills or displaces species or just alters population. You could reduce the population of the species down to be very small without destroying or removing it. So some sort of killing, displacement, or reduction of population size in the community that directly or indirectly creates opportunity for new individuals, new kinds of lower definition has a useful attribute to it that's not really in this one quite as clearly or explicitly, which is that the disturbance event not only changes which species can be there, but it changes the resource availability for the physical environment, which is, of course, what matters to species in being able to grow in a certain place. So a discrete event in time or space that changes populations, usually reducing them, and especially causing changes in resource availability in the environment. One thing that I guess over the last, I don't know, a generation or so of ecology is we've really tried to emphasize that in a certain way, disturbance is a normal part of ecosystem function. Organisms in all ecosystems experience some sort of disturbance regime or pattern of occurrence of disturbances, and also counter types of disturbances. In fact, fire and grazing in the context of concept, but there are other kinds of disturbance events that I can think of. One of the reasons we can think of disturbance as somewhat normal is that many organisms are adapted to disturbance or disturbance regimes, especially when those regimes are predictable in certain ways. If something happens every year, or every few years, or it's regular enough that the natural selection can act on those species and lead them to adapt to certain patterns of disruption. A good example of this that I like from the East Coast and the South is the serotinous plants. So serotiny is just an attribute that many plants have where they release their seeds for fruit following some trigger. And iriscence is a kind of serotiny that is a result of fire. So fire in some plants will cause the melting of the resin in the cone. And once it reaches a certain temperature, the cone opens up and seeds are released. So here's a plant that grows and is adapted to replace with a regular fire regime. And the recruitment of new seedlings is dependent on the occasional occurrence of fire.
Is that why sometimes lizards will like lose their gills? Is that what this is saying?
That generally is a response to predation, adaptation to predation. So if you can survive losing your tail, then you're more likely to have higher fitness after the tail predation. Whereas in this case, it's all about recruiting new individuals of this population of trees following a predictable or semi-predictable disturbance like fire. This is one of several species of pines that does this. Pinus rigida, pitch pine, which grows all throughout the East Coast, and I got to see it in Delaware. So I was a grad student in Maryland, where we have a place called the Pine Garden, vast forests of pines that are dependent on fire. Another one I really like, we'll come back to next time, I suspect, is that many ferns, especially in tropical environments, are adapted to disturbance in terms such as landslides, exposing bare soil, moist bare soil, and then certain species that are introduced by ferns will colonize very quickly and spread across the whole hillside. You've got Baptisia ferns all across here, this is all fern, and even tree ferns growing up very rapidly. So we've got one more slide to show you. Hurricanes are a classic disturbance event, especially in the southeast, increasingly far north. When you think about plants in the southeast, what kinds of trees do you think of? Along the Gulf Coast, let's say. What kinds of trees? Yeah, tall palms. Palms are actually quite good at withstanding the kinds of physical forces that are applied by hurricanes. They have straight, bendy trunks and not a lot of other branches that act like sails. And the fronds at the top fold over under high wind to let that wind rip past them. So oftentimes, in a woodland or a palm forest like this, after a big hurricane, many of the broadleaf trees will be knocked down. A lot of the forms will be doing okay right on the coast. So we see some adaptations, or at least some interesting functional relations between certain kinds of plants and disturbance events. And then here is the term I just defined for you verbally a few minutes ago. Is a disturbance regime of the attributes of that pattern, the frequency, the distribution, and the severity and the intensity of the disturbance. So we're going to think about these three sort of axes of variation in disturbance events when we start class or good? Any questions?
Overall, class participation the last couple of sessions has been awesome. Keep it up. Those of you who have been participating and those of you who haven't, up your game.
I haven't. We're getting a point.
Yeah, I know. That's why I'm coming over here.
I didn't talk to you. I've had this shot ever.
Had what?
Video of
Yeah, I haven't got around to sending out the way to get you onto the.
Sure
Yep.
that I wasn't.
No, it's me. It's not you. I mean, that's what she said also. It's me, and that's not you. But in this case, it really is me, not you.
Normally it is me.
After I turned it in on Moodle last class, but
Okay.
after we talked about it and went over it, I read it.
All right, good, great, awesome. I wasn't planning on being there. What do you need to talk about?
A little bit about the paper.
Oh, yeah.
If not,
Yeah.
I can come Monday morning.
Yeah, let's do that instead.
Okay.
What time's good for you?
Okay. I'm gonna say 10:30.
10:05. I'm out of class by 10:05.
Okay, that works.
So just come in. Yeah. All right. Cool. Thanks. I'm glad that you're reading it early. You gonna send me an appointment request?
Yeah.
I got Caden for today, didn't I? Yeah, I got Sadie. That's who I was looking for. I don't know what's gotten into everybody the last couple of days. I guess they've finally hit their stride.